Okay, we're going to be working number 55, and things are a little different here for these last 4 problems. So what we're given is that y prime plus 2y equals some function of x. And then we're told that the function of x is a piecewise function. And in this particular example, it's 1 whenever x is between 0 and 3, including both 0 and 3. And it's 0 if x is bigger than 3. So what we're supposed to do is find a continuous function satisfying each differential equation and the given initial condition. So we also want that y of 0 equals 0. Okay, so let's take a look at, what's happening on the interval 0 to 3. So on that interval, the function f of x is equal to 1, so our differential equation becomes just this. And that, we've done this over and over, so should be comfortable seeing that this is just e to the 2x for our integrating factor. And now we know the left side is the derivative with respect to x of our integrating factor times y. And that equals 1 times the integrating factor, so just e to the 2x. And then we go ahead and integrate both sides, so we get e to the 2x times y equals, we're integrating both sides, so we get 1/2 e to the 2x plus some constant called c1. And let's see, we know that if we divide through, we get y, which is some function of x, is equal to 1/2 plus c1 times e to the negative 2x. So just dividing both sides there by e to the 2x. But we also have the initial condition that y of 0 has to be 0. And since we are looking in this interval, right, where x is between 0 and 3, we can actually solve for what c1 would be. So we know the left side must be 0 whenever we plug in 0 for x. So we get this plus 0 into here, that would give you just c1. So that tells us that c1 is equal to negative 1/2. So here's what we've got. We've got that on this interval, our function of x is going to be 1/2 minus 1/2 e to the negative 2x. Okay, that's on the interval 0 to 3. Now what we do is we're going to kind of start the problem over again, and we're going to say that if we're looking on the interval where x is bigger than 3, then our differential equation becomes y prime plus, what the heck is that? Okay, never mind. Plus 2y equals, well, now we're on where x is bigger than 3, so if we go back to up here to our piecewise function, our function must be 0. So this must be 0, and we already know our integrating factor is e to the 2x. So we know the left side, so nothing changes here. Left side is going to be e to the 2x times y, but this time when we multiply the right side by the integrating factor, we just get 0. And that means e to the 2x times y must equal, when we take the antiderivative of both sides, some other constant, c sub 2. So dividing through by e to the 2x, we get c sub 2 e to the negative 2x. Okay, so here's what we've got. I'll just say y is some function of x. The thing is, we cannot plug 0 into this because we're not looking on the interval that has 0 in it. We're only looking where x is bigger than 3. So what we have right now is a function. We're trying to come up with an overall function, which we can call y. Let's just say y. Right now what we know is this. on the interval 0 to 3, we know it's, where is that thing? It's 1/2 minus 1/2 e to the negative 2x. And on the interval where x is bigger than 3, we know it's c sub 2 e to the negative 2x. So what we want is to try and figure out what would make this function continuous, all right, a continuous solution. So our discontinuity is happening here at 3, right, when we have a switch over from 3. So what we want is basically that the limit as x approaches 3 of this function, so that means if we're approaching 3, let's approach it from the right hand side, that means we'd be looking here. We want this limit as x approaches 3 to be equal to the function's value at 3, and so if we're at 3, we're going to be right here, so that needs to be equal to 1/2 minus 1/2 e to the negative 2 times 3. Okay, so now we can just take this limit, let x go to 3, so we get c sub 2 e to the negative 6 must equal 1/2 minus 1/2 e to the negative 6. I'll divide through by e to the negative 6, so you get 1/2. When you divide by e to the negative 6, it's the same as multiplying by e to the 6th, and you get that, and then minus 1/2. That should be our c sub 2. So now what we do is, I'm just looking at something, yeah. So now what we do is we come back up here and we replace our c2 with that. So I'm going to do that. I'm just going to save some space here. So in front of that, our c sub 2 we know needs to be 1/2 e to the 6th minus 1/2. So that equation right there, that function of x, it's a piecewise function, will satisfy the original differential equation, which is here, where this function is this piecewise function. So that's it. We are done with that one. Let's look at 56. Just going to follow the same sort of method here. So for 56, we've got y prime plus y equals some function of x. Here we're told that this function of x is again piecewise. It's 1 and negative 1. It's 1 if x is between 0 and 1. Make sure I get this right. And it is, when it's bigger than 1, it's negative 1. And we're given that y of 0 equals 1. Okay. I should have mentioned on the previous problem that this function that we found not only satisfies the original differential equation where f of x is this piecewise, but it also satisfies this initial condition. Okay, so we also had that in there. I forgot to say that. So let's go ahead and go through this again. This is a perfect form that we need. Let's look on the interval between 0 and 1. And I like to use that one first because we know the initial condition is in there, so we should be able to solve for the constant. If we do that, then our differential equation looks like this. We're working in the top piece, so this right side is 1. And now our integrating factor, I'll let you get that yourself. The integrating factor should just be e to the x. So we get that d dx is e to the x times y, and that must equal the right-hand side times the integrating factor. And now we just integrate, so we get e to the x times y equals e to the x plus a constant, I'll call it c1. And we divide through by e to the x, we just get 1 plus c sub 1 times e to the negative x. And now we know that we were told that y of 0 equals 1. So y of 0 equals 1 means that this equation up here becomes 0 equals, equals 1. So 1 equals 1 plus, and again, plugging 0 into this, we should just get c sub 1. So that means, is that right? 1, so we should get 0. C sub 1 is 0, is that right? 56. Yes, well, hold on. Yeah, okay. C sub 1 equals 0. That's kind of strange because that means that y is equal to just, if C sub 0 is 0, then that means y is 1. Okay, all right, let's keep going. Now, on the interval where x is, what was it, bigger than 1, our differential equation becomes y prime plus y equals, now it's negative 1 because we are looking here instead. And when we do that and go through the same story, we get d dx of e to the x times y equals negative e to the x, and then we integrate both sides, we get e to the x times y equals negative e to the x, so the antiderivative of that's just that, and then plus some other constant. And so that means that y is equal to negative 1 plus c sub 2 times e to the x, negative x. All right, so now here's what we know about y. Y is equal to the constant 1 function if x is between 0 and 1. And if x is bigger than 1, it's equal to negative 1 plus c sub 2 e to the negative x. And now we need this to be continuous, and we're really only looking at 1 because that's where it switches. So we need the limit as x approaches 1 from the right, because that would put us here, of negative 1 plus c sub 2 e to the negative x. We need that to be equal to what it is at 1, which is 1. And now when we take this limit and let x approach 1, we get negative 1 plus c sub 2 e to the 1 must equal 1. And now I'm going to solve for c sub 2. So c sub 2 e must equal 2. So c sub 2 must equal 2 over e. So I just added 1 to both sides and divided by e. And yeah, okay, so now we know what this c sub 2 is, so I'm just going to come back up it in here and replace it. So we should have here 2 over e. All right, I'm going to just double check that. Okay, I see a little bit of a mistake here. When I plugged 1 into this limit right here, oops, when I plugged 1 into that right there, it should have been negative 1 right there. And that's negative 1, and so this next line should be 2e. There we go. So this should be 2e times that, and you could rewrite that as e to the 1 times e to the negative x is just e to the 1 minus x. Yeah, that would be okay like that. Okay. So there we go. That's it. It satisfies the differential equation, and it also satisfies the initial condition, where the right side of this is this piecewise function. Alrighty, let's look at 57. Okay, y prime plus 2xy. Let me make sure I'm recording. I don't remember if I hit that button. Yeah. Okay, 2xy equals some function of x, where that function of x is x if x is between 0 and 1, and it's equal to 0 if x is bigger than 1. Oh wait, oops, I messed that up. That's less than 1, and this one is greater than or equal to 1. And our initial condition is y of 0 equals 2. All right, so let's take a look at this. This differential equation is in the perfect form. So on the interval 0 to 1. When we do that, we get y prime plus 2xy equals x. And our integrating factor is e to the integral of 2x, which is just e to the x squared. So this left side becomes a derivative with respect to x of e to the x squared times y equals x e to the x squared, multiplying both sides by the integrating factor. And now we integrate with respect to x, so we just get e to the x squared times y equals, over here, this is just going to be, I'm going to let you do the integration on that, 1/2 e to the x squared plus a constant. So I integrated here and here, and then I'm going to divide through by e to the x squared. So we get 1/2 plus c times e to the negative x squared. So that's dividing both sides. Let's call it c sub 1. Now our initial condition is y of 0 equals 2, so that means we're in this interval, so we can get the c1 from here. So y of 0 equals 2 means that that equation right there becomes 2 equals 1/2 plus, and now when we replace that x with 0, we just get 1 there, so we just get c1, subtract a half on both sides, so we get that c1 equals 3/2. Okay. Okay, now going back to where our function was, here's our function right here. So what we know is that y is equal to 1/2 plus 3/2 e to the negative x squared. That's what we got so far. That's only on 0, 1. Now we need to look when x is bigger than or equal to 1. And for that, it's going to, the original differential equation would be y prime plus 2xy, and this time this will be equal to, I believe it was 0. Let's see what this, yeah, piecewise up here it's 0. So 0, we already know the integrating factor is e to the negative x squared. No, hold on. Is e to the x squared, sorry. E to the x squared times y. And we multiply the right side by that also, but that's just 0 still. So this will be nice. This will just be e to the x squared times y when we integrate, and the right side is just some other constant. And so y is equal to c sub 2 times e to the negative x squared, dividing both sides by e to the x squared. So now we know that y will be equal to the first one we got, which was 1/2 plus 3/2 e to the negative x squared, so long as x is between 0 and 1, not including 1. And then if x is bigger than or equal to 1, it should be this c sub 2 e to the negative x squared. So now we want to know what's happening in this transition. We want to make it continuous at 1, so we want the limit as x approaches 1, this time from the left, because we have the equal sign underneath here, so it's defined, the function is defined here at 1, and it's not defined there, so we want to come in from the left side of 1, and that means we want to be plugging into this negative x squared. That must equal the function's value at 1, so the function's value at 1 is going to be c sub 2 e to the negative 1. So that's just going into this one and replacing this x with 1. All right, so let's let x approach 1 on the one on the left. So we get 1/2 plus 3/2 e to the negative 1 must equal c sub 2 times e to the negative 1. We will divide both sides by e to the negative 1, which is the same as multiplying both sides by e. So multiply that by e, multiply that by e, it's gone. And that should be your c sub 2. So if we go in now and we replace this with this, then we will have our function. All right, there's one more. I'm almost there. 58. All right, so we've got 1 plus x squared, y prime, plus 2xy equals some function of x. That function of x is equal to x if x is between 0 and 1, not including 1, and negative x if x is bigger than or equal to 1, and my initial condition is y of 0 equals 0. Alright, so we need to get this in the right form first, so I'm going to divide through by 1 plus x squared. So this function on the right hand side is actually that over 1 plus x squared. That's a little different now, because you got to imagine that this is going to change our function over here. So let's go ahead to get the integrating factor. So e to the integral of 2x over 1 plus x squared dx. I'll let you do that. It's a pretty simple basic u sub. This is e to the natural log of 1 plus x squared. We don't have a domain restriction there because 1 plus x squared is always positive, and that's just 1 plus x squared. Now we multiply both sides by this, and we know that the left side will become that integrating factor times y, and that must equal this side times the integrating factor. Great news. That's just our function of x. So I did this one a little different. Let's look at it on the interval 0, 1. If we do it on 0, 1, not including 1, then this just becomes d dx of 1 plus x squared times y equals x. And now we integrate both sides with respect to x. So we get 1 plus x squared times y equals 1/2 x squared plus some constant. And now I use the fact that at 0, when we plug in 0 for x, we get 0 for y. So I'm just going to do it right now. This left side becomes 0, and the right side becomes c1. So c1 is 0. That's nice. That means, you know, I'm going to kind of go back. Let me go back and solve for y. Okay, so y must be, let's see, x squared over 2 times 1 plus x squared. So I divided this guy right here by 1 plus x squared, and then I'm going to divide c1 by that. Now I'll replace y with 0 and x with 0, and you'll get c1 is 0. Okay, so if you do that, you'll get c1 has to be 0, which means that this could be rewritten y equals x squared over 2 times 1 plus x squared, like that. So that's what y is if we're on this interval 0, 1, including 0. Now let's look at what it would be on x bigger than or equal to 1. So on x bigger than or equal to 1, we get d dx of 1 plus x squared times y must equal negative x, because that's what the piecewise function is over there. And now when we integrate, the only difference we have here is 1 plus x squared times y must equal negative 1/2 x squared plus some constant. And we can divide through again, and we get y equals negative x squared over 2 times 1 plus x squared plus c sub 2 over 1 plus x squared. All right, so far we have this guy and this guy. This is what it is on here, and this is what it is here. But we want them to be continuous, so we need to take the limit, and our discontinuity is at 1, so limit is as x approaches 1 from the left, because we're not defined at 1 on this one, of this x squared over 2 times 1 plus x squared must equal this guy at 1, evaluated at 1, which would be negative 1 over, let's see, 1, 2 over 4 plus c sub 2 over 2. That's just plugging in 1 for x. Now when we take the limit on the left, we get 1 over 4 must equal negative 1/4 plus c sub 2 over 2. So we get, let's see, add this to this side, so we get 2/4, so that's 1/2. 1/2 equals c sub 2 over 2, multiply both sides by 2, and we get c sub 2 equals 1. So if we just come back up here and replace our c sub 2 here with 1, then this would be the first part of the function, this would be the second one. Let me just double check it here. They didn't. 3/2, what the heck? Yeah, that should work. Okay. So we are done. Thank goodness. All right. Hope this helps.